Promise, we are giving a bunch of updates on some astronomy news today. And in our first topic, the last time we did one of these actually in class, we talked about a new kind of supernova called a superluminous supernova. And the one we talked about was the brightest supernova ever observed. That was in February. Well, guess what? It's not the brightest anymore. We now have a new brightest supernova. We're going to talk about that one today because it turns out it's a different type from the kind we talked about last time. This thing was actually detected first in 2016, but it took a while for the astronomers to analyze all their data and to realize that it was indeed the brightest one they'd ever seen. And so they just published a paper about it, and we're going to talk about that. This one occurred in a galaxy which nobody even noticed the galaxy before. It's 3.6 billion light years away. And so when the supernova was detected, then looking at supernova, they picked up the galaxy as well. Supernova was first detected by one of the survey telescopes. This one's called the Pan-STARRS, which I forgot what it stands for. It's some kind of an acronym. Pan-STARRS Survey Telescope. It's on the island of Maui in Hawaii. And we've talked about it before. It was the survey telescope that detected the interstellar asteroid, Oumuamua. And it finds a lot of stuff. So it picked up this supernova image in 2016, and after the astronomers had been looking at it for a while, they realized it was something special. And so they started looking at it with other telescopes. And down here at the bottom, we have some of those images. The one on the left is from a telescope in Arizona called the Multi-Mirror Telescope. And it's just a picture, the image that the telescope got of the supernova. Now you can see it's real. All you're looking at there is a bunch of pixels, really. Since this thing is 3.6 billion light years away, it couldn't really resolve it in any real sense. It's just aware, okay, there's bright light coming from there. And then they used the Hubble, and with the Hubble, they were able to see the entire galaxy in which the supernova exists. There's where the supernova is in relation to the rest of the galaxy. And then here's another image with a different camera on the Hubble. Again, there's the galaxy, and there's where the supernova is. Now, I want to point out one more thing. As I said, the supernova was originally discovered in 2016. This Arizona telescope thing says it's at 362 days. So this is almost a year after the supernova was first detected. And that's because it took them a while to realize, hey, there's something special here. We need to know more. We need to come back and look at this thing again. And the first Hubble image is more than 1,000 days after its first, so almost that'd be little under 3 years after it's first detected. They looked at it with a Hubble. So here's a couple of charts that tell us something about this supernova. The one on the left, these are the supernova light curves. And they're shown for a whole bunch of different wavelengths of light, indicated by the different colors. And you'll notice that some of them are brighter than others, as they're putting out more energy, but they all have roughly the same shape. They come soaring up, they hit a peak, and then they have a very, very slow decline. Now, down here, those numbers, those are Julian days. Some of you may be familiar with Julian days. It's a way to combine years and days together. So this one is at 57,400 Julian days. You go back and figure that out. For some reason, they're starting their calendar that date back in the 1950s. I could not find out why. But at any rate, we look at that, like here's 57,400, here's 57,600. So this is 200 days after this point. So we see it's beginning to decline there, but the decline really is slow. You get all the way over here, which is 800 days. So over 2 years later, it's still pretty bright. It's going down, but it's quite bright. So this is one thing that indicates how bright this thing was, that the light intensity persists for such a long time. This other diagram shows us a couple things. They think that this was, and we'll talk more in detail in a minute about exactly what kind of star this was that blew up. But we've discussed in the past that this is definitely a core collapse supernova, where in the core, at the center of the star, you get this iron core, so it can't do fusion anymore, and gravity crushes everything in, and boom, it blows up. But before any of that happened, what typically happens in the life cycle of a giant star is a lot of material gets ejected from the star before the supernova ever happens and goes floating off into space. And what this thing down here is telling us, the CSM stands for circumstellar material. So that's stuff that got pushed out from the star. 40 to 150, that little symbol down there stands for the mass of the sun. So from 40 to 150 times the mass of the sun is stuff that was pushed out away from the star before the supernova ever happens. Then we come into here. This is where the supernova is actually exploding. And you see here, 50 to 180 times the mass of the sun. So the part of the star that's left that actually blew up is at least 50 times, maybe up to 180 times the mass of the sun. So what we've got here is one monster of a star, just enormous, when you throw in the stuff that has already been pushed out, plus what's still left. And then also this contributes to the brightness, because when the explosion happens, all that energy comes pouring out. And out here somewhere, when it hits this stuff that's already outside the star, it illuminates it, and so you get even more brightness. So that's why this supernova was so bright. Now, the first couple of points here are the same things we just talked about, but what we're going to talk about now is what they think, what the nature of the star actually was, because it turns out they think that it was quite unusual. Because if we, as I said before, if we add up what was left in the star and what was already pushed out, it's just enormous. It's just a really, really, really big star. Well, there's one problem with that, and that is astronomers have got this theory of stellar life cycles, and we talked about that in astronomy class. And the bigger the star is, the more likely it is to have burned up all its hydrogen long before it becomes a supernova. So if the star was actually this big, there shouldn't have been any hydrogen. But when they do a spectral analysis of the light, they see hydrogen. So the question is, why is there hydrogen when the star is so big? Well, the astronomers came up with a theory. And what they think is that this thing started out as a binary star system composed of two big, big stars, but not enormously huge. These stars were not so big that they had lost all their hydrogen, but they were in a binary system, and they were very, very close together. And eventually, they actually collided and merged, and they made a new star which was incredibly big, but still had some hydrogen left in it. So it's this huge star then that had the supernova explosion, and it turns out there's a different explanation for this supernova than from any we talked about before. This is what's called a pair instability supernova. And here's what that means. Because the star is so big, most of its energy gets sent out in extremely short wavelength waves. That is, it's mostly in the gamma rays. Now, this is something we know about all stars. We know, of course, our sun, most of its energy is in visible light. Some of it's ultraviolet. There's a little bit in X-rays and a little bit in gamma rays. But as stars get bigger and bigger, the reason why we talk about big blue stars is that as stars get bigger, they produce a lot more ultraviolet, which is more energetic as shorter wavelength. And so the star looks blue rather than yellow like our sun looks. If we go the other way and look at red dwarf stars, they're red because most of their light is in the long wavelengths, which is in the red or even infrared region of the spectrum. But truly enormous stars will have a lot of their energy as gamma rays, which we talked about that before. Gamma rays are the most energetic part of the electromagnetic spectrum. And it turns out that gamma rays have a peculiar property that doesn't occur in any of the other wavelengths we talked about, not in X-rays or anything else. Gamma rays have so much energy that quantum mechanically they can do a very weird thing. We're all familiar with Einstein's equation that says E is equal to mc squared. Energy is mass times the speed of light squared. And we're used to thinking of it in terms of what happens when we do something that destroys mass and produces energy. For example, nuclear fusion in stars, or nuclear fission in reactors, or atomic bombs. And in that case, mass is destroyed and energy is produced. But quantum mechanics says, hey, all the equation says E is equal to mc squared. You can also get mass from energy if you have enough of it. And it turns out that gamma rays contain so much energy that it's possible for a gamma ray photon to spontaneously turn into an electron-positron pair. So instead of being light, it'll suddenly turn into a pair of matter particles, an electron and a positron. Now, what will normally happen is those things will not stick around very long. The electron and the positron will collide again and annihilate each other to produce more gamma rays. But what happens in a star like this, where most of the energy is being produced in gamma rays, is that it's possible at some instant, enough of those gamma rays will have split into electrons and positrons that, and now we have to go back to, I'm hoping people remember this. We talked about stars being in hydrostatic equilibrium, meaning that their fusion energy is just enough to balance the gravitational compression that's trying to crush them down. Well, in these huge stars, it's gamma rays that are producing that energy. If enough of the gamma rays happen to, at some instant, turn into electrons and positrons, all of a sudden, they're not producing the radiation pressure to reduce gravity. So gravity gets a chance to just crush the star to the point that it blows up in a supernova. That is your pair instability supernova. And that's how this monstrous supernova happened. Okay, so to the best, well, two things to the best of knowledge. Number one, when we talked about the superluminous supernova, we said, is one of them going to go off and kill us? And we did some analysis of what causes that to happen. Said, nah, not likely. There are just not any stars that are close enough that are likely to do this. Fortunately for us, it's even less likely that we'll be anywhere near a pair instability supernova, because it requires you to have a binary system of two really big stars. And we certainly have lots of those in the Milky Way galaxy, but most of them are located in toward the center of the galaxy, and we don't have any around us. So that says that we're pretty safe from this. We don't have to worry about something like this happening nearby, and we all get fried by a supernova. We've got other problems to deal with, so we don't have that one to worry about. Okay, so before we go on to our next topic, any questions about this? If not, you can always ask at the end. So let's move along. About a year ago today, we talked about the Event Horizon Telescope, which is basically it's a name for a group of people and a telescope that they created by combining a bunch of radio telescopes. And they used that Event Horizon Telescope to take the first image of the shadow of a supermassive black hole. It was a supermassive black hole in the galaxy M87. Now we know, of course, that we can't see black holes. They're black, they don't emit light, but there is light all around them, and so they do cast a big shadow. And we're going to show that image again in a minute, so if you've forgotten it, we'll bring it back up. But what caught my attention was there are a couple of papers published this month by members of that group. And I wanted to talk to you about them because they're both quite interesting. One of them is just purely theoretical. Some of the people in the group looked at Einstein's theory of general relativity, and they used that to say, hey, if we could make our telescope more sensitive, we could get a much cooler image. And the reason they say that is this. When we talked about general relativity, we mentioned that it predicts that light passing close to the sun or any other star will get bent by the sun's gravitational field. And you recall we talked about that was how general relativity was first observed. That I'm sorry, I got a mistake here. It's in 1919 that eclipse was, not 1918. In the eclipse of 1919, astronomers actually observed this bending of light as it went past the sun, and that's the first observational evidence that Einstein was right in his theory. Now, the gravity of a black hole is much, much stronger than the gravity of the sun, so not surprising to think that it can really bend light. And in fact, it can bend light so much that we get something that looks like this. This is a figure that shows here's a black hole, and here's light coming in towards the black hole. Now, if the light is coming in like this, it just like matter, that light's going in the black hole, we won't ever see it anymore. But the light is coming in like this, so it's close to, but not inside the black hole event horizon. The gravity of the black hole is going to bend that light, and it'll take it right, it'll just orbit around the black hole, and it'll go shooting back out again. So it's going back wherever it came from. And the same thing will happen to light that's a little further out and a little further out until eventually way out here, when you're far enough away from the black hole, the light gets bent but doesn't come back. So it just goes off in that direction. Uh, well, imagine this. Suppose that you're out here, like on the right-hand edge of the screen, and you're looking right in at the black hole. Then what you ought to see, as this light circles around the black hole, you ought to see a ring of light. As this light goes around, we should see it going in and out like that. So we should see rings of light around that black hole. So these astronomers said, hey, you know, we don't see that, but if our telescopes had more resolution, we could see it. So what they're saying is that the current radio telescopes that make up the Event Horizon Telescope don't give them enough resolution to detect this. But if they were able to add some more telescopes, in particular, if they could launch some radio telescopes out into space, then they ought to be able to see, they think at least the inside ring ought to be visible. And so here's, again, this is the image that they produced. So the inside of this donut is where the black hole actually is. And so what they're saying is, if they can add some more radio telescopes, we ought to see bright rings right around here. Well, at this point, it's a theory, okay? I mean, you know, they're working from Einstein's theory of relativity, and nobody has said there's any problem with it, so it's probably right. But we don't actually know whether it's true or not, and we won't know until we're able to get these radio telescopes up into space so that we'll have enough resolution to tell whether this really goes on or not. No, this is the actual black hole image. Okay. Now the other paper concerns some more observations that have actually been done with the Event Horizon Telescope, and that's looking at something different. That is looking at the quasar. It's called 3C279. We actually talked about this quasar when we talked about active galactic nuclei. It's one of the more well-known quasars, puts out an enormous amount of energy, but it's also known that it puts out these jets of material. And we've had pictures of these jets before, but they've never been anything like this. These are taken with the Event Horizon Telescope, and they give us the most detail that we've ever seen. And the reason there are three pictures is they actually took them using three different wavelengths of radio wavelengths. This is 7 millimeters, this is 3 millimeters, and this is 1.3 millimeters. And notice they're taken actually on different days. Okay. So what are these jets? They're coming out away from the black hole. How can that happen? The black hole is supposed to swallow everything up. Well, there's a theory for that, of course. Astronomers think that what's going on is that the black hole, in addition to everything else it does, creates a really strong magnetic field. And that magnetic field is perpendicular to the black hole. So that when that material revolves around the black hole on its way to getting sucked in, some of it gets caught up by the magnetic field and follows those magnetic field lines. And so instead of falling in the black hole, it gets shot out in perpendicular to the black hole. And so that tells us that we should have jets of material that go out on either side of the black hole. Now, if we look back at our picture, we only see one side here, but that's because this particular quasar is pretty much pointed right at us. so we can't see the jet that goes out on the other side. We can only see the one that comes toward us. Now, also, astronomers are able to verify that because this black hole has such a huge magnetic field, that these jets travel at 99.5% of the speed of light. So that stuff that's coming off, which is just some kind of particles, is traveling almost as fast as the speed of light, which is really amazing. Now, that also might make you worry a bit. I said this thing's pointing at us and it's shooting out all this material with these enormous speeds. Do we need to worry about that? Well, actually, we don't. And the reason we don't is that 3C279 is about 5 billion light years away. So while those jets look kind of focused right there, by the time they travel 5 billion light years, they will spread out and go in, every possible direction. So we won't ever see any real significant amount of material coming at us out of 3C279. Okay. All right. Our next story, we're going to look at some news from Mars. And this is really more about what's happening right now with some Mars missions, given the current circumstance. And it's kind of interesting. We're first going to look at the Curiosity rover mission. We've talked about the rover itself before and the work it does. We haven't really talked about how it's controlled. Well, under normal circumstances, there is a mission control room in the Jet Propulsion Laboratory in Pasadena, California. And it's just a big room that has large video screens up on one wall that show what the rover's doing right now. And then in the room, there are a bunch of individual computer workstations for the people who work there to monitor the output of all the scientific instruments, make sure everything is functioning as it should. And then right outside the mission control room, they have some little meeting rooms where teams from this control group can meet and plan their future activities. Well, of course, right now, none of that's going on because just like we're all at home, they're all at home too. However, here's a picture of a bunch of these folks sitting at home, and they're working from home. And of course, here's Curiosity rover. You might say it's working from home too. It's just still out there on Mars like it always was. But to me, what's just totally amazing, I mean, we're sitting there at home in front of our computer and we're watching classes and we're doing this and that. These guys are looking at Mars. And it seems to me I would just love if I was working for them right now, because if every day you got to look at Mars, it would make life a little more interesting anyway. But they're actually able to control the rover and have it carry out its mission just as if they were in the mission control room. The project website says they're keeping almost the same schedule of activities that they would do if they were working in the old way. And in fact, just in the end of March, they were able to actually guide the rover through the process of drilling into a rock and analyzing the material that gets pulled out. So this is the kind of thing they would do normally from the control room, but they were able to successfully do that even working from home. Now, next, we're going to look at a future mission, the 2020 rover, which is now called Perseverance. And pretty much the same, those folks are also all working from home. And here you see a picture of lots of them working from home. The that's a picture of that's an artist's conception of what the rover will look like once it's on Mars, but of course it's not there. However, not all of these people are working from home, and the reason is they can't be, because this rover is still being put together, and of course they've got to be where the rover is, and right now it's still at the Jet Propulsion Laboratory. Now, the reason why people have to be there working on that is this thing has got to launch from a period from like the middle of July through the middle of August. It's actually only a 3-week period. And you recall, we've talked about this before also. That's because if we look at the orbits of the Earth and Mars, then and we're going to see a picture of that in our next topic, so you'll maybe understand a bit better then. But this summer, the Earth and Mars get relatively close together. And so if you want to launch a mission to Mars and be able to get it there and not spend $1 jillion on fuel, you have to do it now. So if they can't get it launched right now, they're going to have to wait 2 years before they can launch this thing. That's because it's only every 2 years that the Earth and Mars get relatively close together. Actually, slightly more than 2 years. So some people have to work on the physical task of doing the final assembly of the rover, and then getting it put into the nose cone of the launch vehicle, and eventually going to get it shipped off to Kennedy Space Center. But there's also work going on at Kennedy Space Center right now. And so some of the members of this team have to go back and forth between California and Florida. Now, obviously, you don't want to be, if you have to go regularly back and forth between California and Florida, you don't want to get on a commercial flight. Because you don't know who's on there. You certainly don't want to get infected with coronavirus because somebody on the plane had it. And so these trips are being made using an Air Force transport plane. And as each trip ends, then a whole crew goes in and the whole plane gets totally sanitized before the next trip, so that the people who are doing this travel are safe as they can be. Now, once they get to Kennedy Space Center, the work they're doing there is in what's called a clean room. That's where the final assembly is done on the nose cone and the rocket itself. And it's called a clean room because it doesn't matter what's going on right now. It's always kept as free of any kind of contamination as possible, because they don't want to have any bacteria going along with this mission to Mars, because we don't want to put bacteria on Mars, because if we find bacteria there, we want to know that, hey, we didn't take them there, that they actually exist there. So the people that are actually working at Kennedy Space Center are about as safe as they can be, because the room they work in is as clean as you can make anything anywhere. Okay, now I'm assuming that the people who are working in the control of the InSight mission are also working from home. Unfortunately, I couldn't verify that. There's nothing on their project website that says so. But it does say that they're continuing to work, and we talked in our special presentation about how they think they finally got the heat probe working, and apparently it's still working, although they're advancing it very, very slowly, because they want to make sure nothing goes wrong with it again. But apparently it's still working. Okay, now here's our next topic. This is an image of an asteroid. It's got this charming name, 52768 1998 OR2. And that asteroid, right now, while we're talking, is going past the Earth. And when in a minute, when we're done with this presentation, I'm going to see if we can switch. There's a live telescope view of it. And I was looking earlier and they hadn't brought it up yet, but I'm going to see if we can switch and take a look at that. This is an image of the asteroid done by the Arecibo radio telescope back on April the 18th. And it shows you a pretty good idea of what the thing looks like. It's a little over a mile in diameter. Well, right now, this thing is about 4 million miles away from the Earth, and that's as close as it's going to get. It's just in the process of coming by the Earth, and it's going to go back out again. So there's no real danger here. But it's worth noting, 1 mile asteroid is a serious thing. If we were ever to get hit by such a thing, it's like the dinosaurs wiped out all over again, except this time it's us. But on the other hand, that's very unlikely because you can see here, you can actually see that there's light reflecting off this asteroid. Anything that big, you can actually see with a telescope. And so astronomers feel like that pretty much all the asteroids that size they know about. They've known about this one since 1998. It's the somewhat smaller ones that worry people because they're pretty much dark and you don't see them until they get quite close. But here's a picture of the orbit. This is the orbit of the asteroid, and here's the Earth's orbit. And you see what's happening. This is where they are right now. The Earth's come around to here, the asteroid's come around to there, and then the asteroid's going to go on off. And it's about every 5 years that it comes close to the Earth like this, but it's not going to come close again anytime soon. In 2070, right now I said though this distance looks close, it's 4 million miles. 2079, it's going to be only 1 million miles, but even that's 4 times further away than the moon is. And also, as I mentioned earlier, notice here's the orbit of Mars. And you see what's happening. The Earth is coming around. Remember, the Earth travels a lot faster than Mars does. Our year is 365 days, and theirs is 687. So it takes them a lot longer to go around the sun, so they're traveling slower. So what's happening is the Earth's coming around this way, and so by July, it'll be down here, and Mars will be right along here somewhere. And they'll be about as close together as they're going to get. So that's why it's really, really important that we have this mission launched middle of July through the middle of August. Because if we have to do it, we have to wait 2 years for them to line up again. Okay, so next topic. We've talked about gravitational waves before, and we talked about the LIGO Gravitational Wave Observatory. They just announced last week a detection of a pair of colliding black holes. Again, this actually happened. They named these things GW, stands for gravitational waves. 19 was the year. This happened last year. It happened about a year ago, in fact. It happened April 12th of last year. But they're only announcing this result now because it took them a while to process the data and verify what actually happened. Well, they've detected lots and lots of black hole collisions, so you might wonder what's special about this one. And what's special was the black holes involved. In most in all of the previous collisions of black holes, the size of the black holes has been fairly close. They're like if one was 30, the other be 40. If one was 45, the other might be 52, something like that. Here, then those are in terms of masses of the solar masses. In this case, one of them was 30 times the mass of the sun, and the other was only 8 times the mass of the sun. And so that's notable because number one, it's the first time this has happened. And number two, it allows astronomers to verify something else about Einstein's theory of general relativity. It's that theory, of course, that predicts that we'll detect gravitational waves. But in the case where the two black holes have very different masses like this, it says that whereas normally when two black holes collide, you get a single frequency of output, in this case, you actually get two frequencies. So you get what we call harmonics. And if you're a musician, you know what a perfect fifth is. It's a chord you can make with a couple of notes, and I forget right now well what the notes would be, but there are a couple of notes that you can hit that make a perfect fifth, so it sounds harmonious to our ears. So interestingly enough, the gravitational waves produced by this collision actually made a perfect fifth, which is just kind of a interesting little sidelight in this. But mainly it interests astronomers because they were able to predict it would be there, and the data actually shows that it's there. Okay, so one more image we want to look at. This is the 30th anniversary of the launch of the Hubble Space Telescope, and they took a special image that they put out to celebrate that, and that's this one right here. This is an image of two gas clouds. They're actually a part of what's called the Large Magellanic Cloud, which is a satellite galaxy, which unfortunately we can't see. You can only see it in the southern hemisphere. But these are two gas clouds in that satellite galaxy. This one is the blue one is actually produced by a single star. This is one of those huge blue stars, and just like we were talking about the one that produced that supernova, pushing out a lot of material before the supernova, that's what's going on here. This is material pushed out from that blue star and making this big cloud around it. This cloud is what's called a star-forming region. It's actually a cloud of molecular hydrogen gas, and these bright lights are stars that are in the process of coming into existence within that cloud. Okay, so that is the end of the presentation. Before I take questions, I want to switch and see if we can get this picture of this image of the asteroid. Nope, looks like it. They were saying, I guess they did not, let me back up. Nope, not there. They were saying that it might, they were having cloudy skies and they might not do it. So I guess that's what happened. We might have seen a picture of it, unfortunately we're not. So apologies for that. So let's just end that. And sorry. Try this one more time. Okay, so do we have questions? If you want to unmute yourself or...
Yes. Hey, Bill, this is the Ratliffs, and for whatever that matters. But a meteorite could be either from an asteroid or a comet. Is that right? Technically?
Yeah. Most of the big meteor showers we get are actually cometary debris. You know, if you see a comet, you know, it normally has this tail, and that's, but as a comet gets close to the sun, the heat of the sun causes material to basically break away from it, and that's what forms the tail. And then that stuff eventually can break away from the comet, and that's what makes the meteor showers, is that material that actually comes from comets. So you're correct, it could be either one.
So we can worry about comets and we can worry about asteroids. Are there other orbiting objects out there? I mean, the way I understand it, those two, they're kind of like, there's specific definitions apparently of their composition. So are there other things floating out there you can fear?
There's nothing really close enough. There is a third type of thing that exists out in what's called a Kuiper belt. And those are things that they call icy objects, which are basically like asteroids, except instead of being rocks, they're big hunks of frozen stuff. In a lot of cases, just plain water, or it could be like frozen nitrogen or frozen carbon dioxide or stuff like that. But those things, in order to be in that state, they've got to be way, way out. Oh. So if one somehow gets deflected, so it starts coming in our direction, long before it ever got close to us, the heat of the sun would basically break it up. So really, you know, the only stuff we got to worry about is asteroids and comets, and of course, possibly the totally undetectable little tiny black hole, which there can, you know, theory says there can be such things, but it's not. You should worry a lot less about them than you do about asteroids and comets, because there shouldn't be that many of them, and they are tiny. We're talking small. We're talking like stuff the size of baseballs. And so even if there is such a thing and it comes close, it's probably still going to miss us, just because this whole thing of space is really big. And if a little tiny object like that comes by, it's just, chances are it's just not going to come close to us.
Just so I can remember, you said the icy stuff, as you called it, is in the Kuiper, not the Kepler, the Kuiper belt?
Kuiper belt, yeah. Kuiper, I'm pretty certain is right, yeah. It's the area that's outside Neptune's orbit.
Oh.
So it's pretty, that's where Pluto is. And a bunch of other, see, Pluto is basically a large icy object. There are several other what we would now call dwarf planets out there besides Pluto in that region, but there's also a lot of really small stuff, you know, stuff like a mile or 2 miles or even smaller. And it's mostly just a bunch of frozen something or other.
Thank you.
Okay. Any other questions?
Okay, Bill, I have one.
Yeah.
Okay, so we're looking at the black holes, and they have 3 dimensions, right?
They do.
They do have 3 dimensions, and so when the light is reflected around them, I mean, so it's going all the way around the 3rd dimension, right?
Right. Yeah. It's kind of like imagine like say a basketball, and light coming in, and so it would go all around that ball. And that's and actually I'm glad you said that, because I realized that makes it a little easier to understand why what we could see would be a ring. It would be because that light is, as you just pointed out, in 3 dimensions.
Right. Okay.
So it would come to the projection would come to us as a ring. Yeah.
The basketball was a good image. Okay. Thank you.
Okay. Other questions? Well, I hope everybody's having a nice day. We are, let me, we mentioned last week, next week we're going to take up a new topic, which is biology. And we'll do, the first lesson is going to be on evolution. And I still don't know if I'll do 2 on evolution or not. I may. There's a lot of stuff there, and I want to cover it thoroughly. We'll do either 1 or 2 on evolution.
Not virus evolution, I hope.
I'm sorry, what?
Not virus evolution.
Yeah. Yeah, well, hopefully, that's the one, so far, that thing doesn't seem to have had significant mutations.
Is this good or bad?
Yeah, well, who knows? I mean, yeah, well, mutations are mutations, and so they can go either way.
Yes, that's right. It seems pretty sturdy on its own.
It does indeed. It doesn't need to get stronger, that's for sure. But at any rate, we'll have at least 1, maybe 2 lessons on evolution, and then, as I mentioned, we're going to do a quick 1 lesson return to artificial intelligence, because we want to talk about this thing called genetic algorithms, which is an artificial intelligence technique that got developed because some people studied evolutionary biology. So that just fascinated me. And I figured I had to talk about that. Then we'll return to biology. But then, of course, as usual, at the last Wednesday in May, which I haven't looked at the calendar, I don't know whether we have 4 or 5, but the last Wednesday in May, we'll come back to astronomy. And we've already got at least 1 topic reserved for that, because some of you may know Victoria pays as much attention or more to astronomy than just about anybody. And this morning she emailed me and said, "What do you know about this?" At the time I didn't know anything about it, but I've looked at it, and it's something else about black holes, in fact. And we'll talk about that at the end of next month when we do astronomy again. So I hope everybody is continuing to have a nice day, and I look forward to seeing you next week.
Cool. Thank you, Bill.
Sure.
Thank you, Bill.
Bye-bye.
Bye.
Bye. Thanks, Bill.